Thanks everyone for being here. So today I'm going to introduce a new library from the field of topological data analysis, Scikit TDA. Been working on this for the past couple years. I'm not going to give a complete, thorough introduction of topological data analysis, nor a complete introduction to Scikit TDA. There's a lot to cover, so I'm going to try to give just a steel thread of some of the most interesting facets of both. A little bit of background. Before Scikit TDA, I started my master's 2 years ago, and a wide-eyed graduate student trying to understand TDA, apply it to all of the data sets. I found that there was lots of different tools, all in different languages with different overlapping features. And if you wanted to use a particular feature, you had to step into a completely different programming language. After Scikit TDA, there's now lots of different tools plus one. This started out a collaboration with Chris Tralley, who's a postdoc at Duke University, and Hendrik van Veen from Nubank in Brazil. We were hoping to curate tools, curate lots of different implementations. Every grad student wrote their dissertation, published their one script of code, and then walked away from it forever. We picked up a lot of these, packaged them under one API, one system, made them easy to use, and put them on GitHub, easy to contribute to, and easy to install. You can install it all with Scikit TDA. There's lots of documentation to get started. If you're a mathematician and don't really know how to code, it's really easy to get going. If you're a computer scientist and don't really know about topological data analysis, there's a lot of background, so you can start to understand a lot of some of these ideas. It's also very easy to contribute to. We try to be really responsive on GitHub. And we have stickers, so if you come to the sprints tomorrow, there's still a couple left. I think as a testament to what we've done in the last couple of years, we have over 25 contributors that have all contributed to some aspect of the project, either documentation or pull bug requests or entire new features. So I'm going to give a brief introduction to topological data analysis, not the entire field. I'm going to focus on persistent homology. There's lots of other aspects. I spent most of my work working on Mapper. And there's also lots of really great work in sheaves. Leland McKinns is here, did UMAP, also built upon some very similar ideas. I'm going to walk through some controlled examples, looking at data sets that we know the topology of and seeing what the results are. And then dig into a very interesting application of anomaly detection. So you might have heard something about coffee cups and donuts, not to be confused with cops. Topologists study shapes, holes, and connectivity. We say that the coffee cup is equivalent to the donut because you can transform one into the other while still maintaining the essential topology of the object. There's still a hole you can put your finger through and grab onto it. Topological data analysis is the way we take these theories of shape and holes and move them to data. We can now estimate that there's one hole in this point cloud data using these tools. You might ask why you care about holes. Well, if you're ever doing clustering, you're actually looking at zero-dimensional holes. It might be hard to wrap your head around. It was for me too. But by laying that foundation of what holes are in the lower dimensions, we can build it up into higher dimensional holes and look at much more complex behaviors. So you can understand what a one-dimensional hole is. A loop shows up in maybe time series cyclical behavior quite a bit. There's also things like voids. The empty space in the middle of a basketball is a two-dimensional hole. These show up in material sciences a lot with porous materials. And there's also tons of combinations. I can't show you a 14-dimensional hole. If I could, I would. But we can add two-dimensional holes and one-dimensional holes and get toruses and much more interesting objects. So the way we go from data to topology and apply the topology is by building something called a simplicial complex. It's a generalization of a graph with triangles, tetrahedron, and higher up into higher dimensions. The way we build that is that every data point becomes a vertex, and we strap a ball around every vertex, and every time those balls intersect, you draw an edge between them. If 3 balls intersect in one place, then you draw a triangle between them. And so this builds the simplicial complex that's much easier to work with than lots of different data points floating around. And by looking at this final construction, it still captures some of the structure of the data points, But we can easily calculate that there are two holes. Those two triangles aren't filled in by the blue triangles. We'd say there's two holes right there. So the problem is that one radius can be misleading. Depending on which radius you have, there's going to be lots of different results, lots of different topologies. A radius of 0, you're going to get the topology of your original data set, and a radius of infinity, everything is going to be connected together, so it's not going to be very meaningful. And the entire spectrum in the middle, it's not very stable. So the way that we account for this is by looking at all the radii. By looking at the entire sequence and counting the holes at every level, every point in that sequence, we can look at the entire global structure of the holes. And that gives us persistent homology. We're able to, so what this is showing is a barcode of the homology at each sequence, each step in the sequence, where every time a hole is created, so the loops, easiest to understand, are the H1. So every time a hole is created, a bar is created, and every time the hole is filled in, every time the balls get so big that all of the triangles fill in the gaps, the bar is destroyed. And so the longest bars are the most persistent, and the shortest ones we can attribute to noise in the data set. So H0 is capturing the zero-dimensional holes, or the groups, the clusters, and H2 is capturing the two-dimensional holes, the voids in the center. So this is the main workhorse of topological data analysis. So I'm going to walk through a couple of controlled examples. Hopefully it just lets us sink in a little bit and actually see some code, show how we can use Scikit TDA to do all this for you. We supply one package called TDA sets that supplies some very easy to use constructors like loops and spheres, toruses. We have some Klein bottles, and all in high dimensions. Here we have a one-dimensional sphere as a loop. There's a little bit of noise added onto it, and then RIPSR is our main persistent homology workhorse. It's one of the fastest algorithms out there, and this is computing the persistence diagram. It's similar to the persistence barcode, but by converting it, instead of showing when the bar is created and then when it's destroyed as a bar, we're showing each bar as a point, with the created time is the x-axis and the death time is the y-axis. So points that are very far from the diagonal are more persistent, and things that are close to the diagonal we can attribute to noise. So what we see here is that the one-dimensional holes, there's one point very far from the diagonal. The zero-dimensional holes, there's always going to be one point out in infinity, because no matter how far you grow, there's always going to be one connected group. That's not as interesting to look at, but we do see a little bit of noise down there at the bottom. And we're using PERSIM that handles all of our plotting of diagrams and comparing of diagrams. So here's a two-dimensional sphere, or a sphere, and computing the persistent homology of this sphere, we see that there are some points in the H1, so there are some one-dimensional holes, but they're very close to the diagonal. They're very small. But there's one point, a two-dimensional hole, very far from the diagonal. So this is capturing that. This is telling us that there is one sphere in this data set, but not any other structures. We can move on to a torus. And so here the torus does have two one-dimensional holes. It might be kind of hard to wrap your hand around. There's one hole, so the two one-dimensional holes are shown here, one that goes around the arm of the torus and the other one that is like the hole that you can actually put your finger through. And then the two-dimensional hole is the actual empty space inside the torus. And so in red, we're seeing that there's one hole far from the diagonal, or farther from the diagonal than the noise, and the two-dimensional holes is a little bit further. Or the two one-dimensional holes are also a little further from the diagonal than the other points. So we can compare these diagrams. It's easy to look at a diagram and see that there is some features on it, but you can also look at the data set if it's low enough dimensions. Being able to compare the diagrams will let us actually apply the topology and use the persistence diagrams as a feature, maybe in a downstream machine learning task. So what I'm showing here is the Wasserstein distance. It comes from optimal transport. It's kind of the theoretically best distance, but is a little slow to calculate. We also have a lot of other distances that are much quicker, but all approximations of the Wasserstein distance. So I'm showing 3 loops here with varying levels of noise, and then just plotting the one-dimensional persistence diagram for each of these loops. So, and then comparing the first loop, which is just a perfect circle, with the second one, and then the first one with the third one. And we can see that the distance between the first and the second is much smaller than the distance between the first and the third. The way this is working is it's matching all of the points in each diagram together, and then computing the Euclidean distance between the sum of the distance between each of the pairs in the matching. So the most significant, all of the points near the diagonal, they're very small. They contribute very little to the distance, but that green line is showing the distance between the 2 most significant points. So I'm going to move on to anomaly detection. So I just started a job at New Relic. We do monitoring of the internet, consume a lot of signals about software. And a lot of data sets we have kind of look like this. Some sort of time series that is sometimes periodic, sometimes not. And I'm interested in, can we detect an anomaly in this time series? It's very easy to see if there's like a max, or, if something diverges significantly. But in this case, the periodicity just dissolved. There's a strong signal every minute, and then it just went away. So can we use TDA to detect this? Well, let's see. So to start out, we're going to have to do a little bit of pre-processing on this signal. The idea here is we can look at the autocorrelation curve and take the largest non-zero peak, and that should tell us about how long the period is. It doesn't have to be exact. So we're going to build a sliding window embedding, which is pretty stable. So looking at the autocorrelation peak, we can estimate it's about 8 units. I just scrubbed the actual units off this data set. But so 8 points, and each period is shown here. There's 13 periods in this signal. And it doesn't have to be exact, but we get pretty close, we can see. So then the sliding window embedding, this is a really cool concept that I've been recently introduced to. The idea is, so say you take a sliding window of 3 points, and the y values of each of those 3 points become the x, y, and z values of a single point. And you start with the 0th, first, and second point, and that becomes a single point in 3-dimensional space. And then you move to the first, second, and third point, and that becomes also a point. And looking at the signal, it creates this interesting object that then we can use, because now this is in like a nice metric space that we can compute topology on. So computing that sliding window embedding on this signal, we're taking 8 periods, using, again, RIPSR to compute the persistence diagrams. So 8 periods at a time are shown here, and then we're sliding those 8 periods 1 period at a time over the signal. And in the beginning, you see that there's this loop, right? So this is 18 dimensions. We're just visualizing it with PCA, bringing it down into 2 dimensions so we can actually see what's going on. But then computing the persistence diagrams on the 18-dimensional space. So when the signal starts moving into this kind of noisy regime, you can see that loop degenerates into a corkscrew. It kind of spirals out of control. And it happens pretty quick. So you can see that period right there, right? And there's a 1 point far away from the diagonal on the persistence diagram. And then wait for it to go around again. You see again, there is that point drifts down towards the diagonal. Or yeah, right. So there's the periodicity kind of falls apart. Yeah. So we can watch we can watch that persistence diagram, and that's really telling, but we still want a way to automatically detect that, that something is happening, right? We don't want somebody like sitting on a monitor looking at persistence diagrams all day. Just, they could just look at the signal, that's fine. So using the watch design distance again, what this is showing is comparing the third frame in that video with the fifth frame. That's the diagram on the left, and the third frame with the eighth frame. So both of those, the first two are still within that regime of strong periodicity, and the signal is still consistent. Those diagrams are very close. You can see that matching. The matchings are shown in green, and the distance is just about 45. So there's just a little bit of noise there, a little bit of differences, but not much. And then it drifts into frame 8. That's where there's 2 frames now, or two signals worth of data that there's no period. And that point has drifted all the way from the diagonal, and now our distance is 280. So that's a gigantic difference. The watch design distance is great because it doesn't matter what your topology is. A lot of people just use like the distance of the max point or the length of the max bar. So what you would see here is that like the distance, you would just be looking at, so the bottleneck's distance would just be the distance between the farthest distance between points. So it'd be just those 2 points you'd see the distance between, the 2 points farthest from the diagonal. But if you have lots of different topological features, like say your signal is actually like 4 loops, or there's some like some signals actually sit on a torus, but this would still be able to pick that up and see when the topology changes. And what was actually a little surprising to me is this this was surprisingly fast. When you're looking at one-dimensional holes, like 2-dimensional holes get a lot slower, 3-dimensional holes get even slower, but making these graphs took a lot longer than computing anything that is shown in the graphs. So this could work in real-time detection. So there's a lot of things I did not cover that I wanted to. So there's Mapper. I spent a lot of my time working on. It's a way of looking at high-dimensional structures and bringing them down into very low dimensions, kind of like dimensionality reduction, but it gives you a kind of skeletonization of your object that you can play around with. This is really popular in industry. There's a company, IASD, that has applies these a lot in the healthcare industry for understanding data. UMAP, like I mentioned earlier, is built on top of a lot of the same theories that all of these tools are coming from, but is used for dimensionality reduction. And there's a lot of really cool applications of TDA for machine learning. I showed you like how you can use the persistence diagrams for computing differences in the topologies. There's also persistence images that you can feed directly into neural networks and other vectorizations of these objects. And there's also some really cool examples of people actually looking at the topology of neural networks and showing that like the topology is actually important in the training process. Tomorrow we'll be doing the sprint. If anybody wants to help out on or learn more about this software, I would really like some help with getting Scikit TDA on Conda Forge. We have a Python package that is proving to be troublesome. And if anybody knows anything about release processes and automating those, that'd be a lot of help. There's also a lot of cool work with, we're trying to work on a new visualization for the barcodes, and lots of other documentation fixes and stuff. There's a lot of help, and if you come, you can get a sticker. So a big thank you to Chris Tralley and who started this workout, and also Leland McKinn's kind of inspired a lot of this work, and all of you for coming. If there's any questions, there's some resources here. The slides are posted online if you want those. Yeah, that's everything.
So raise those hands. Yes.
Yeah, I just wanted to confirm, so the higher the Wasserstein distance, that's when an anomaly is taking place?
go back to that slide where it's 3 to 8.
Yeah. So the Washington distance is measuring the distance between the diagrams, right? So when the diagrams diverge a lot, that Washington distance will go up, and so it's like
And that's when there's an anomaly?
well, that's when we can tell that there's a big difference, that the periodicity changes. So like if you can just kind of imagine calculating in your head, it's pretty stable. The distances are very small, and then they change considerably, and then it's pretty stable again. So there's that shift that, I mean, we could classify it as an anomaly, or maybe just change in the periodicity would be more exact.
So the sliding window concept is really cool, and you used 3 here to put it into 3 space, but I wonder, like, why not 2 or 4? Or like, what are the implications of that decision?
Yeah. So I said 3 because it's. Oh, so he asked about the sliding window concept. So here it's shown in 3 dimensions. Why not 2 or 4 or some other number? So I said 3 here. I think this is a little bit higher actually. So what you want is the sliding window to be the length of the period. So here we use 18 because that's how many points we estimate are in one period. And then we're just visualizing it in, like, using PCA to bring it down into lower dimensions so we can see what's going on. But I've also found it's very stable. So as long as you're within like half of a period and a period and a half, you're going to get pretty stable results.
I'm a total newbie to this kind of thing, and it looks so beautiful. And are there any tutorials or things that you would recommend to kind of ease into it and try to understand?
Yeah, so scikit-tda.org, we have a lot of tutorials on all of the different methods, lots of notebooks that are both online, or you can download and like walk through yourself and make changes and stuff if you'd like. We've worked a lot on making the content very approachable, so we've tried. Yeah. So yeah.
Yeah, you said you're using PCA, but I see a time series. So where's the dimensions by Lockton? I couldn't see it. So this time series, where's the dimension?
So we're using the sliding window embedding, where we take 18 points, and that now, or 18 points in the time series, and that becomes one single point, where we're just taking the like the y value for each of those points, and that's becoming so the y value of the first point is x, and then the y value of the second point is y, and so that'd be a 2-dimensional point, and then taking the sliding window over that and making that embedding that way. So that's how we can go from the time series on the top to the yeah.
Why use MPCA and not UMAP or Anomaly?
PCA works really well on like this small example. You could probably use UMAP. It might turn out better. I don't know. Yeah, quick and easy.
Can you go the other way? So you're looking at like typically point clouds and seeing like what their quality is. If I have the point cloud, can I figure out another point to add that would improve like various topology quantities? So like could I make it a better circle, for example, or a better one piece? Can you repeat the question for the recording?
He asked if so if you go the other way, like if you have a point cloud, like you can compute the topology, the persistence diagram, but can you maybe use that information to change the point cloud so that it like improves the diagram or improves the topology? I'm not familiar with them. I think there are methods to do that, like in 3-dimensional space. Like I know, like if you're taking 3-dimensional images, you can then like fill in the noise. You can see like where the little tiny holes are and fill that in. I think off the top of my head, I don't know anything exact. Be a great research question. Oh, yeah.
Sorry, I came in late. Maybe I missed it. The source code for this is on GitHub, right?
Yes.
I just looked on the GitHub and it seems to have the init version. Doesn't seem to be complete. Is that
Which,
Scikit
so
TDA package?
so if you go to github.com/scikit TDA, so that's where all of our code is.
Okay.
Yeah, the content for the slides are available at this link, but this repo is not public yet. But yeah.
All right, if there are no more questions, let's give Nathaniel a big hand.
Good to meet you.